Okay, hi everyone. This is the Open Sesame talk, and in 3, 2, 1, flash. So introduction, I won't present you Synactive because my colleague already did. You did, but I will talk instead about myself. Lucas Georges. This is my real name, obviously. I'm a reverse engineer now for 10 years, French. I'm not really a public person, so maybe because I live in the cultural shadow of some certain someone. But you may have known me for the dependency tool that I've wrote a few years back. I used to be pretty knowledgeable about Windows security and Windows internals, but I think there is some Windows expert here in the attendees. I feel like Windows expertise is going the same way Flash expertise went 10 years ago. It was on everyone's name, and then Steve Jobs happened. So instead of just keeping on Windows security, I ventured a few years ago on different realms of security, which are mobile security, embedded and security, or firmware security. So on this basis, let's get to physical security. So what is physical security? It's mainly people know two parts of the physical security aspects. The first part being perimeter protection, aka walls and gates. The second part are access control, which we'll talk about in this hour. But there are another aspect of physical security, which has remote surveillance, intrusion detection, incident response. Basically, you want, in the physical space you're protecting, you want to have some view of what's going on, and you want to know, pretty much like network security, if you are breached, and if you are breached, you want to have a team that can respond to it. And the last aspect, which is quite overlooked, but interesting nonetheless, is infrastructure protection. Infrastructure protection is like a scenario where an attacker can just shut down the network, the grid network, or the electrical power lines running in your building, and then your intrusion detection system and your remote surveillance are in the dark, literally. So it makes sense also to protect this infrastructure. The main objective of physical security are deterrence. Same thing with your protecting your bike. You don't need to buy the best bike lock to protect your bike. You just need to buy a lock that is better than your neighborhood bike. And the second objective is intrusion slowness. Given a sufficiently motivated attacker, you may want to give as much time as needed by the incident response to act on a breach. But here we are just focusing on access control. So, access control. Here is a lovely hand-drawn graph made by myself. So the access control is a red thing. Basically, it's a device that when a user presents itself to it, grants or denies entry to a physical space that is protected by the gray walls. The more simplest access control devices, usually the electromagnetic door you can see on Airbnbs, are access control and modder fused inside the same device. But the more sophisticated, the more secure way to do it is to use a controller that is usually remote, either on the network or just hidden in the basement or something like that, to send the signal to open the door. So what's the purpose of access control? There are two. The first one is identity verification. You want to ensure that the person that is presenting itself in front of the door is the person is telling you him to be. So there are two ways to do it. The first one is authentication, pretty much like a web server. So you need some secret, passcode, passphrase. Or another factor is a smart card that is usually enrolled. And as a second factor, nowadays we usually use biometry. So somewhere on this card there is a fingerprint of your fingerprint that tells the system that you are the owner of the card. And then the second purpose, which is also quite interesting, is time and attendance recording. Since you're protecting a physical space, you want to have a log of people going in and out. That way, if you have a breach or something weird, you may want to see if there is any discrepancies within this log. So here in this talk, we'll focus on the IDEMIA Sigma Lite Plus device, which is an access control device made by IDEMIA, which is a French company. It's formerly known as Morpho, for those who knows. It's probably not known outside of France, but it's pretty, I won't say common because it's a high-grade access control terminal. It costs about the cost of an iPhone. But it's usually present in high-end targets like airports, train stations, embassy, ministries, and Fortune 500 companies, which are part of our client at Synactive. So that's why we are interested in this device, because we encounter our pentest team, which do intrusion detection, and red team also sometimes encounter this kind of device. And they were wondering what they could do with an employee badge, if they could just swipe it and entering some facility with it. So they asked me. It was like 2 years ago. So if you don't know, this contactless cloud usually have Deathfire enabled. If you don't know Deathfire, it's okay, because we won't talk a lot about it in this hour. But you have to know that Deathfire works in the way that it's like folder and files. They call it application, and within those applications you can write and read file. That way several devices can use the same smart card because they have their own little garden where they could read and write file. And here, when I read an employee badge using a Proxmark, we can see that by default, the employee badge has only one application. So the bio application, which are the ID 42494F, which probably meant biometric information was stored in this application. And the second information is like the key is 2 TDA, so it's a triple DES. And you have to know that to read the file, you need to be authenticated. So you need to know the key. The terminal, the device knows the keys, but we don't know. We try to read the application 0, which is the master application, with the standard key 0, and it doesn't work. And same thing for the application bio. We try to read the first file, and with the same default key, it doesn't work. And so I studied the reversing journey. The thing is, like most embedded devices, this one has an upgrade file format that is public, but it's encrypted. But in reality, it's not encrypted because the upgrader decrypts it on your desktop. So I managed to get the firmware upgrade in plain text and then unpack it. And then I got the function that is responsible for managing a bit like everything. And it's a BMOS, it's a ginormous application with 10,000 of code, a function in IDA. So I said to myself, well, this is not going to work. This may be going to work, but it will take like at least 3 weeks to find the correct function that is doing the derivation of the key. to know exactly which key is written on the contactless badge. So instead, I had an idea, is to gain arbitrary code on the device, because sometimes a little session with JDB attached to the process is way faster than 3 weeks of reversing. I'm not saying that's a good idea, but that's the idea I got. And sometimes you have to follow your shot, you know. So I started by hardware. You'll see in the next slide that hardware security is really not my thing. This is a photo of the back panel of the device. So this is a part of the device that is facing the wall. So we see on the red dot, we see a classic application processor, which is an IMA6 from NXP, running ARM 64-byte, I think. It's a pretty common CPU that we can find on the automotive ECU, something like that. We have on the bottom, we have the contactless sensor and the biometric sensor that communicates with the application processor using FTDI. And funny thing, we have an USB port on the front panel, so something is that can be accessed by an attacker. But a colleague of mine told me that he saw some test pad on the right bottom of the image. So he told me to test some signal. Little bit of soldering, and yeah, I found the UART output log. Unfortunately, I didn't find the UART input port. Probably is deactivated on the production units. And that's it for hardware hacking. Sorry. So I just switched to bootloading. The way the device boot is really standard for embedded devices. We have our bank A and bank B. The bank A is the nominal mode, the one that's working, that checking the contactless badge, something like that. And the bank B is the upgrade mode. One thing interesting here is that the bootloader, whether it's bank A or bank B, it's the same, it's a U-boot. And it does, before loading the partition from the flash to the RAM and jumping on kernel, booting the system, it does partition checking. They have the custom signature check on the partition. And another funny thing is, like, before jumping on kernel, they also do a secure boot check using the secure core of the AME6 CPU. So it's like belt and suspenders. You have to be doubly able to sign the partition to be able to boot a custom kernel, which is pretty good for an embedded device. The partition check is pretty simple. It's just a blob of data that is signed by RSA using SHA-256 for RTGest. And the only vulnerability I could find here is, like, there is an hard-coded 1024 RSA bit key. So it's now it's becoming kind of weak, but it's not that weak that we, at least, can break it. Just to look back on this partition check, every partition on the left is checked by the partition check, except the UBFS-A. The userland file system for the nominal mode is not checked because it's mounted as read-write, and some application write into the rootfs. So there was maybe a scenario where you could, I don't know, desolder the flash, try to modify it and rebuild it some way. But I didn't do that because I was just terrified of breaking the device, which I almost do anyway. But I didn't want to go to my boss and say, I burned a device, can I get another one? So instead, I looked for the upgrade mode. Why? Usually the upgrade bank is simpler than the nominal mode. It doesn't mean that there is usually more vulnerability in it, but at least it's part of the code that you can just take a look at it pretty quickly. So the upgrade mode is pretty usual for an embedded device. The kernel is uncompressing itself and launching some kind of hard-coded initramfs. And the file system that is decoded only has two applications, discovery app, which is low boot to try to discover other IDEMIA devices on the same LAN, and the map server, so the upgrade server. One interesting tidbit here is like the Linux version of the kernel is pretty recent. I did the research in 2022, and the Linux kernel was from 2021. When they upgrade the system, they upgrade the bank A and the bank B. So they override the upgrade bank, which is pretty mental to me, but somehow it works. So I looked at map server. The executable does really nothing. The only thing is it does open the libmap secure retrofit SO, which is an upgrade server implemented its like language, which is really doing pretty much all the job needed. There is 3 ways to push an upgrade on this device. The one I used mostly was through the Ethernet port. There is a server, TCP server, listening on the port 1981. But at some point of my research, I don't know how I did it, but I broke the bank A, so I was stuck on bootloading on bank B. And I broke also the TCP server, so I didn't have any way to upgrade the system and come back to a nominal one. So I tried to frantically look for any ways to refresh my system. And there are 2 ways to upgrade it, to refresh it. One through an USB device that I didn't find to identify. I think it's probably a custom device that IDEMIA's technicians have. And also you can upgrade, pushing an upgrade through an SD card via the USB on the front panel. That's why it exists. It means for soft brick device in production, they can always refresh it through this USB front panel. The binary upgrade format is really from the 90s. Everything is from the 90s actually. It's a TLV style, so we have our magic 1, 2, 3, 4 for the command, and then based on the second short of the command, we have different server commands available to us. This is a list of the commands that are implemented. We'll focus on the bolded one, parameters on read, parameters on write, and retrofit validation. Parameter zone because it's a read-write, obviously. And retrofit validation, it's a command that the client sends. It sends like a manifest of the firmware upgrade he wants to push, and then the device says, "Oh, you can't upgrade from this version to this version, or you can downgrade it, or something like that." The parameter zone. So it's a zone that it's a persistent memory zone within the flash. It's a JSON file basically, but in the memory, and there is a lot of variables that are used for persistent configuration, like Ethernet MAC address, default LAN IP, something like that, and the package part number, package firmware version. And as I said, using the previous API, it's read and writable by an attacker. So I thought to myself, it's pretty nice. I think the developer didn't expect for an attacker to be able to write and read and write from this part of the NAND. and probably will use it as trusted inputs. So I've constructed a little data flow of where it's used, either in bank A or in bank B. I didn't manage to find any vulnerabilities in how the data is handling in bank A, but in bank B there are several executables that have vulnerabilities in it because they trusted the way the data is formed. Mainly discovery app and lib check retrofit. And what are these vulnerability? It's uncontrolled string copy calls. The funny thing on the string copies in discovery app is like, so there are string copies which led to stack buffer overflow, but the function never returns, so we can exploit it because the function we don't have access to the return pointer on the PC. So instead, I tried to exploit it on the libcheck retrofit.so. So how it works, as an example, the SO calls this function called check device information with the different parameters that is sent by the client. So the client sends the part number, the firmware version you want to flash, and the hardware version you want to flash. And using the information, the libcheck retrofit.so want to check if there is if it's possible or not. And it does it by checking the following variable: min firmware version, min gradable version, and CIE part number. And how it populates this buffer. Using getFileList, which is a CJSON API to get the list of value when you give it the JSON key, and is string copy the value return in the output buffer. So here in this case, temp.value is coming directly from the parameter zone, and the output buffer, as we can see, is a statically allocated buffer on the stack. So it's a stack buffer overflow. You have seen it probably many times. As you know, string copy is kind of annoying because it only allows you to have one null byte in your copy. But since we have 3 times the same vulnerability in the same function, we can have several null bytes in our payload. So I tried to exploit it. I didn't try on the real terminal because I don't have access to some kind of debugging setup. So I had to build the exploit completely blind. So instead I tried to emulate it first. As you can see, we can quickly gain control of PC because there is no stack cookie in the upgrade server. But there is a but. As I said, the MAP server executable doesn't have any SLR, but have the NX bit set, but it's a matter of option. But the problem is the MAP server is extremely tiny. It has only 4 kilobytes of code and 200 bytes of data, which gave us a whopping total of 69 gadgets to use without having to have some kind of info leak for gaining access to another gadget. So I really tried to exploit it, but I think I didn't have a single gadget which allowed me to store information on a register I controlled, but doing so I trust 4 registers. So that was the then done. I tried hard for 2 days and I say, boy, sometimes you have to find a better bug, you know. So I tried to find a better bug. And that's why I switched to nominal mode. In reality, I did a lot of back and forth. The vulnerability research is not always straightforward. So how does the device work in nominal mode? Basically, everything is dedicated to the green block, which is a user-run executable called core app. And it's the core app that I've shown you previously, which has 10,000 of functions. So when you map the attack surface, you have the following elements. So the first one is we have a web server and listening on port AD that is used to managing user, enrolling user, something like that. And then we have a Swift port that is more low level and more is used by the technician to reflash something, to change some algorithm. If you don't know Apache Swift, it's like protobuf. Basically, it's a serialization, deserialization format framework that can be used in different programming language because it's generating stubs. So I try first to find vulnerabilities in the web server because it's a light HTTPD web server with CGI. Usually it smells bad, but I didn't manage to find any because they were pretty smart about it, or maybe they had a lot of bug bounties on it. Nowadays, what the CGI does is they take the user parameters, they serialize it into a valid Apache Swift message. They send the message to the Apache Swift server, and then they get back the answer, deserialize it, transform it into a valid HTTP answer, and then show it to a user. So it's just a proxy. There is no real data handling here. Same thing for the Apache Swift. You'll see, a low-level RPC access. Probably there are a lot of things that were not were privileged or not checked about an attacker. The Apache Swift implemented something like 150 messages, so it's pretty big attack surface, but everything is written in C++, so it's a lot of reversing work to do to be able to find a vulnerability here. And even though it's C++, the string copy, string manipulation, data manipulation were handled pretty well. So there was no glaringly obvious vulnerabilities here. And I didn't want to spend too much time trying to find a vulnerability here. Same thing for the USB port and Wi-Fi. Usually it's a last resort way. You prefer to have some kind of application vulnerability before really looking into the system one. And then the biometric part just didn't do anything because I don't know how to attack a biometric sensor. And the last thing is the contactless sensor, because there was attacks on it in the history. So how contactless work for the IDEMIA SigmaLite device? So in this graph we have the contactless card, the peak on the bottom. We have our core app that doing everything, and they use to communicate with the contactless sensor, the PCD. They use a SDK which calls Spring Prox, which I find it when reversing the core app application. The Spring Prox SDK is written by a company called Spring Card. It's a French company, I think. And they publish their SDK on their website. And you can see the last version published was in 2016, which is now almost 10 years ago. Deathfire API is really simple. It's like 15 different API you need to implement as a reader to correctly read the card and write a command on it. I think the command in red need to be authenticated and the command in green don't need to be. And the only API we are interested here in this talk is the DustFire get version, which it's a command sent to the card to get the manufacturer ID, the product ID. And how it works. This is the code from Spring Procs. So it's called df get version on the card using RF commands to do it, and then it waits data from the card. And the thing is, in DustFire EV1, the first specification, the card, the data frame that can be sent by a card is pretty limited because the card doesn't have any power. And then the card can only, I think, send up to 64 bytes in a frame, counting the CRC, I think. So how can the card send more than 64 bytes of data? Is setting a marker on the first bit, which is the marker on first byte, which is called def additional frame, which tells the reader, hey, I have still data to send, and on the last frame, it doesn't send the marker, and the reader knows that to exit the loop. You may have seen the mem copy. Here on the reader just accepts any data sent by the contactless card without any bound check, and it's written in a receive buffer that is statically allocated on the stack. So here we have a beautiful, beautiful Stack Overflow that never happened now. And by the way, same pattern, different vulnerability on the DustFire read data X function. So it's an API to read data from the contactless card. The receive buffer here, since we don't know the size, is mallocated, but there is the same loop waiting for additional data, mem copy everything that the card is sending to the reader, and then it's just erasing everything on the heap. So here are the two CVEs. The heap buffer overflow is scored way lower than the stack buffer overflow because the DustFire read data X need to be post-authenticated, whereas the DustFire get version, it's in this context, is pre-authenticated. So exploitation. I wonder to make this part, and do I really need to explain to OffensiveCon attendees in 2024 how to exploit a stack buffer overflow? But here it is. The checksec on the binary returns that the binary has an NX bit set, so it's a Rob chain problem, so it's not really a problem. It doesn't have any SLR because why should he have? But he has stack canaries, and that is a problem. Because I don't have any info leak, I just have some way to overflow the stack. But in reality, when you look at the function when compiling IDA, where are the stack canaries? They are not present. I don't really know the exact reason. I didn't ask the IDEMIA developer, but either they use the makefile from the Spring Procs SDK, or they link directly the precompiled library from Spring Procs. But anyway, in both cases, the SDK is not compiled with the stack protector on the C flags. So there is no instrumentation of stack cookie inside the function that is compiled by the SDK, even though there are stack cookies everywhere else on the binary. So too bad for them, good for me. So there is still a question that, okay, we have stack buffer overflow, but we need to send, like Thomas Roth said yesterday, those magical magnetic waves. And how we do that? We use a little bit of tool which is called the Chameleon Tiny, made by Proxgram, which is a pen testing tool used to emulate IRAF cards. And the thing is, the firmware is open source. I think it's it's the main repo, the MSEC repo, and some lively soul on the internet already implemented the old Desfire implementation. So I didn't have any work to do in this way. I just need to hack something on the firmware. So the exploitation strategy is, we have eruption. I didn't need to have a full-blown exploit with context execution restorement. I just need to have some system call with the first argument that is control. So here how it's implemented. First step is like we fill out the stack buffer with junk, and we set the status additional frame on the first byte. That way we keep the reader reading. On not the last frame, but the frame before, the penultimate one, we set our eruption, which is just to get jet chaining. Still setting the status additional frame. And on the last frame, we have our payload, which is just a reverse TCP shell on the server. Because as I said, I just needed to have some access, some root access on the device. Okay, so now is the demo. Okay, that's it. It's not my computer, so I'm afraid to break things. So on the left side, you will see a terminal with the reverse shell listener, and on the right side, you'll see a video of me holding a phone, trying to film the attack. So it's going to be pretty quick. Up, and that's it. That's already. And do I film with my left hand while typing the command on my right hand? Maybe. And so we have root on the device, and when we exit, we crash the system, and there is a process listener which reboot the device. So how they fix it? The Desfire get version that was vulnerable was used to detect the smart card. There is a lot of logic because there are a lot of different smart card type that is supported. So you try to find it's a MyFair, it's a Desfire, it's a Calypso card. So that's why it was a pre-authenticated attack. So instead of fixing the vulnerability, they just wiped the call. Instead, they tried to do some select application. So they try to read the master application, and if the card is not returning the correct error status, it's like he said, oh, yeah, it's not a Desfire card. So it's a way to fix it. Okay, and to conclude, first conclusion is like the impact of this attack. First thing first, we can, since we have RC on the device, we can enter the physical space that is protected by the device, which is bad. And another thing that is bad also, it's like we can pivot on the network security network, usually attached to the access control device. And in most time, the network security is adjacent to the global security, and sometimes the same network. So usually it's privileged access to the network. A little bit of timeline. The vulnerability research timeline doesn't make any sense because it's a lower intensity research project. It's something I did between mission on off days. So I started on 2022. I found the first string copy call vulnerabilities on around June, July. I stopped because it was summer. And then I got back on September, October, and that's when I found the Deathfire vulnerabilities and I exploited it. And once we exploited it, we disclosed it to the IDEMIA CSERT. The response was pretty good. We were a bit scared because embedded devices security usually don't have the best security posture. But in this case, they did a lot of effort to improve the security posture. So we have several talks with the IDEMIA security people and developing teams to report the vulnerability, to let them understand what the fixes were. However, since it's an embedded device, the release cycle are pretty long. It's like 3 months, and we just missed a release cycle, so it's like 6 months instead. So we had a private firmware sent to us in May 2023, confirming that every vulnerability that we disclosed were fixed. And since they have to give some advance notice to their client, only on September 2023 the public firmware were published, as well as the advisory, which is here, and the version that fixes this vulnerability is the 4.15.5 on the Sigma Lite and Lite Plus. So now you have to find another vulnerability to try to break it. And that's conclude my talk. Thank you for listening, and if you have any question, it's now.